So, one of the many things on the post-Alien Biospheres to-do list is to make a better map for Tira 292b, the planet that Alien Biospheres takes place on. Because if you've watched Alien Biospheres, then the map that you're seeing on screen now should be pretty familiar to you. This is the style of map that I've used throughout the whole series, and it is, partially by design, extremely crude and vague. Because, as I've said many times, the whole point of Alien Biospheres was to cover the natural history of this planet in very broad strokes. The main purpose of the series was to get a very rough idea of the natural history of this planet before what we're arbitrarily calling the present-day time period. And to that end, working out the nitty-gritty of individual climate zones was never really necessary. You know, climates only really came up in the series when they were directly relevant to one of the topics that we were discussing. So the only real thing that needed to be showed on the map was just a very general indication of, like, oh, you know, somewhere over here there's a rainforest. Or, hey, you know, in this part of the world there's a big desert. And plus, the map changed every episode as well, and each episode already took a prohibitively long time to make as it was. So it wasn't really an option to take an extra month or two just to work out a more detailed climate map, only for it to immediately change again the next episode. You know, that would have just been way, way more trouble than it's worth. But now that we finally reached the so-called present-day time period, and we know that we're not going to be advancing any further forward in the timeline, give or take a few tens of thousands of years at most, then we can finally go in and make a properly detailed map. And in general, we can talk about the planet in much greater specificity. So in some of the upcoming videos that I have planned, rather than talking about the clades very generally like I did in the main series, and just say something like, oh, there is this clade and they live in rainforests, and that's about it. We can now say, here's this clade, here's a bunch of different species of this clade. Species A lives in this particular patch of this rainforest, whereas species B lives further to the south in this area where there's more precipitation or what have you. And we can assign species to specific regions, and we can flesh out the whole planet on a much more detailed, granular level. So the first step of doing that was making a better map. So, for the past month or two, as I've been writing the script for the first episode in the domestication/agriculture/general anthropology series that I'm working on, I've been working to turn this map into this map, which I hope you'll agree looks a fair bit better. Now, I'm not even going to attempt to get into the specifics of the methodology that I used to work all of this out, because if you want that, you can go and watch Artifexian's videos, or Madeline James's world building guide, or go and read World Building Pastor's blog. They go into exhaustive, excruciating detail about all of the steps involved, and I tried my best to follow all of their guidance as closely as possible. So if you're looking for advice on making your own maps, just go and look at all of their stuff. I'll have links to all of them in the description. They can explain this stuff way, way better than I can. And above all, a special thanks to Ross Bay Geo, who is the unsung mastermind behind a lot of the methodology that Artifexian uses in his videos, and he's also helped out Madeline James a lot with her world-building guide, and he was nice enough to answer some questions that I had and to vet this map as I was working on it, and to make sure that I wasn't doing anything grotesquely stupid, so this map would absolutely not be possible without his help. So I'll link to his channel as well. There's not any content on it at the moment, but I have it on good authority that that might change soon. So I would heartily recommend all of you to preemptively subscribe and keep watching that space. So thanks again to Ross and to everyone else whose guides helped make this map possible. And I'll also just say that this map is still a work in progress to some extent. I'm fairly confident at this point that I've got all of the general climate zones in the right place, but I still might make a few tweaks here and there. So don't be surprised if over the course of the next however many videos you spot subtle adjustments to this map, especially once we start going into the regional level and I have to zoom into some very specific area of the planet. I'm going to do my best to make sure that I don't have to retcon anything I say in the videos. Like if I say in a video like, oh, this species lives in this rainforest. I'm not going to say in the next video like, oh, just kidding, they actually live in the tundra. Everything I explicitly state will be more or less set in stone. but there might be some subtle adjustments in areas of the map that the episodes don't specifically touch on. So I'll only actually commit to the details of any particular region once it becomes relevant for an episode, if you see what I mean. Okay, enough preamble. Let me take you through some of the steps that I took to get to this point. Again, I'm not going to go over the exact methodology, just all of the prerequisites that were necessary to get this final climate map. So the very first step was to get a better idea of the topography and elevation, because on this map we really don't take elevation into account at all, other than the fact that we say that these dark grey areas are mountains. And I had a vague idea of how tall the relative mountain ranges were, but that was never specified at any point in the series. So to work things out more rigorously, I had to take a closer look at what the tectonics were doing. Now granted, this is still a very scruffy, loose map. I haven't bothered thinking about the shape of the oceanic plates, just the ones that concern our land masses. Again, extremely basic compared to what, say, Artifexian and Worldbuilding Pasta do. But it's serviceable for our purposes, and there's always the possibility of going back in and fleshing out more stuff later. So, back in episode 1 of Alien Biospheres, which was the collab I did with Artifexian, we had a tectonic simulation that spanned roughly 200 million years or so, which was the time span that I knew that Alien Biospheres was going to cover. So it was only really necessary to think about the tectonics within that time frame. And I should say that I did not design the specific shape of the land masses. That was all Artifexian. All I did was give him a rundown of the major tectonic occurrences that I needed to happen for all of the things that I wanted to talk about. You know, I knew that I wanted to talk about allopatry, so we had to have a continent breaking up. I wanted to talk about biotic interchange, so we had to have some continents coming together. I wanted to have an island continent. I wanted to have a volcanic hotspot. And so he made sure all of those things happened within the 200 million year time frame. So what I did was roughed in where the different tectonic boundaries are, and then label them for which type of orogeny they are, which is what you'll see here, the A, the H, and the L, where A stands for Andean, H stands for Himalayan, L stands for Laramide, and U, which I don't actually have, stands for Ural. And then using Artifexian's Worldsmith spreadsheet, again, links in the description, I calculated roughly how tall and expansive each of the mountain ranges was. And that gave some idea of what the topography of this planet is like, but you'll notice that most of the mountain ranges that we have are along the coasts, which is partially to be expected, but that leaves large chunks of the continental interior that we just don't really have a good idea of what the elevation is like. And so to make the planet more topographically interesting, I actually kind of reverse engineered an older tectonic history that goes back earlier than the simulation we show in episode 1. So that's what these white lines are here. These are inactive or old orogenies. So at the very beginning of the series, we started out with a supercontinent, and that supercontinent would have formed from the collision of several earlier continents. So I've labeled those collisions in the order in which they happened, this 1, 2, 3 here. So first of all, if you kind of ignore this central sea, because remember that is a direct result of the splitting up of the original supercontinent from episode 1. So at the time the original supercontinent formed, this rift wasn't here yet. So if you think of this chunk here as still being attached to this part here, then that would have originally been its own continent, that then a very long time ago, about 350 million years ago, slammed into this chunk here. Then about 50 million years after that, this smaller subcontinent here slammed into the southwestern coast. And then most recently of the old orogenies, sort of the final step in the formation of the old supercontinent, this chunk came down from the north and slammed onto this section here. So taking all of that into consideration, I was able to create this map, and down here we have the scale for it. The color ramp I went with ended up making some of these mountain ranges look a lot more pronounced than they actually are, because this range in the east, which you'll remember is actually homogeneous, if that's the right word, with this little section of mountains here, and it's an extremely old mountain range, which means that it will have had ample time to erode. So looking at the scale, the peaks of this range here would be no more than like 2,000 meters tall at most, which is really not that tall. That's the equivalent of like the Appalachians, for example. So this whole area is more like, a section of rugged highlands than a proper mountain range. Whereas these mountains in the southwest that formed more recently, they haven't had as much time to erode, so they can get up to about 3,000 meters, which still isn't massive. But this northern range here, the most recent of the old orogenies, most of those peaks are within the 3,000 to 4,000 meter range, and I might actually go in and make some of them taller. So these would be more on the scale of the Rockies, for example. There are also these smaller ranges along the coast, which to my mind is a result of the fact that this supercontinent is still sort of in the process of breaking up. So there are rifts beginning to form, and these parts of the continent are beginning to sort of pull away and drift northward. Now Septentria, in its northward journey, has accumulated this rather substantial northern mountain range that gets up to like 6,000 meters. There's also a smaller range along this eastern coast, which I initially had as a much more substantial mountain range, but I trimmed down quite a lot because I really needed to get as much moisture from the ocean as possible into the continental interior. And if I made this range too big, then there would be a sizable rain shadow, which basically turned this entire eastern continent into just one big desert. And I really, really didn't want to do that, so it's still notable. It gets up to 2,000 meters or so at most. But there are some gaps in it for moisture to pass through. But of course, the biggest and most spectacular orogeny is this one in the south, because during the formation of this new supercontinent, what was originally the eastern and western continent have slammed together while simultaneously drifting south. And I've gone back and forth quite a lot on whether or not I want this island to remain separate or if I want it to join with the mainland. In the end, I decided it was slightly more interesting, and it just looked better to keep it separate, but nonetheless, it's still right in the center of this big crunch that's happening here. So this formidable range has sprung up along the coast. And all the way along the southern edge of the supercontinent, we have this range that gets up to 6,000 or 7,000 meters. And right here at the collision point between the two continents, we have this ludicrously gigantic plateau. Everything in white here is over 8,000 meters. As I recall, there's only like slightly more than 100 mountains on Earth that are taller than 8,000 meters, and all of the peaks here are 8,000 meters, some of them significantly more than 8,000 meters. According to the Worldsmith calculator, they could get as high as 11,000 meters. And part of the reason they can get that high is just because this planet just has a lower gravity than Earth. But even so, it's just such an impossibly vast range. I affectionately refer to it as the Mountains of Madness. Also, this ended up not really affecting very much, but I did just arbitrarily make the decision that during the breakup of the original supercontinent, there was this failed rift here that penetrated part way into this section of the continent, but then it failed before it could go all the way through and could actually break off. And so that left this section of very low elevation here. So once I'd worked all of that out, the next step was to establish the ocean currents. So this is the ocean currents during the northern hemisphere summer, and this is the ocean currents during the northern hemisphere winter. So this part was pretty straightforward. It's just a matter of making sure that you have warm currents going away from the ITCZ and cold currents coming back towards the ITCZ, and that they sort of turn and loop back at the appropriate latitudes. And one mildly interesting thing is that because we've got so much land in the southern hemisphere, in fact, here are the lines of latitude so that you can see properly, this is the equator, and because so much of the supercontinent is concentrated in the southern hemisphere, and because land heats up and cools down faster than water, then that means that the ITCZ, the Intertropical Convergence Zone, which is basically like the center of heat and moisture. It's not quite the same thing as the thermal equator, but they approximate each other very closely. So during the southern hemisphere summer, the ITCZ is dragged quite far down, whereas in the northern hemisphere summer, it sticks much more closely to the equator. And again, I was kind of lazy. I didn't bother adding in the ocean currents that weren't going to affect our land masses in any way. And then after that, we move on to working out the wind and circulation patterns. And this, for me, was the hardest step of the whole process. Not because it was particularly complicated or time-consuming. On the surface it's pretty straightforward. The difficulty is that it's so hard to tell if what you're doing makes any sense. Because with a lot of the other steps, there are specific guidelines, like, hey, make sure that this thing happens within this many thousand kilometers of the coast, or within this particular range of elevation, or within these particular temperatures. There's a lot of very quantifiable parameters that will influence where and how you can do things. Whereas with this step, it's just kind of like, hey, draw a blob somewhere in the middle of your continent and have some lines coming off it, and make sure that the lines curve in the right direction, and then try and make the lines join up. And that's kind of it. Obviously, I'm simplifying a lot there, but a lot of it does seem very nebulous. So these are the wind patterns for Northern Hemisphere summer and for Northern Hemisphere winter. And I did have to go back and remake these maps like 4 or 5 times. Because the annoying thing is that basically every single step for the rest of the process hinges on getting these maps right. So there were several points at which I got to the stage of establishing climate zones, only to realize that I'd made a mistake during this step, and I had to go back and start the whole thing all over again. But I think that as we have it now, thanks again very much to the input of Ross Bay Geo, I think that what I have more or less makes sense. The basic gist of it is that, again, since land heats up and cools down much faster than water, during the summer the land will be relatively warm and therefore relatively low pressure, and wind blows from areas of high pressure to low pressure. So this green here, that's low pressure, and the yellow is high pressure. So during the southern hemisphere summer, we have this anticyclone forming in this central sea, and that means we have these strong onshore winds all the way across the edge of this sea and across the northern border of this eastern continent. Whereas in the northern hemisphere summer it reverses, and the entirety of the southern hemisphere pretty much becomes a low pressure zone, and now this whole stretch of the central sea is dominated by offshore winds. So there's some quite strong seasonal effects there, and all of that is instrumental in working out the precipitation map. So you can see during the northern hemisphere summer, this whole section here with the offshore winds is pretty dry, whereas during the summer, and the winds reverse, suddenly you have all of this moisture coming in all the way along the perimeter of this continent. Now, this section here in the extreme east, you'll notice, is very wet both during the northern summer and northern winter. And that's just to be expected because it's smack dab in the middle of the equator, and it's just going to be constantly bombarded with onshore winds. And then we got to mapping temperatures. And the circulation maps may have been the most difficult part conceptually, but temperature mapping was easily the most time-consuming part. This bit took me absolutely ages to work out. So these bands are the different isotherms that represent these ranges of temperature. This is for the northern hemisphere winter, and this is for the northern hemisphere summer. So one of the consequences of having just such a large continent is that the temperature in the continental interior is much more variable. So like during the southern hemisphere summer, we have these arid hotspots that get up to about 38 degrees Celsius, but then in the winter they become much colder, and this eastern one specifically goes down to somewhere between 10 to 5 degrees. And as part of this temperature step, I had to work out the continentality of the land masses, which is basically a measure of how much seasonal variation in temperature there is. And at the outset, when I first started working on the continentality, I was pretty thoroughly convinced that we were going to end up with a hypercontinental zone, which is basically an area that has just ridiculously extreme swings in temperature. Like some parts of northeastern Siberia are like 20 degrees in the summer and negative 40 in the winter. But both Artifexian and Ross Bay Geo pointed out that this land bridge is actually narrow enough to interrupt this continental zone. And if that's the case, then this section of continental zone is not large enough for there to be a hypercontinental zone. So the temperature variation is still pretty extreme, but it's not that extreme, which I'm quite pleased about because that would have made working out these isotherms much, much harder. And also, while I'm at it, the top of this gigantic plateau during the winter gets down to minus 76 degrees, which again is kind of to be expected with mountains of that size, but damn, that is cold. But the main reason this step took so long is because of the checking stage, which, if you watch Artifexian's video where he goes over the methodology, once you establish the baseline isotherms, you can check to see whether they make sense by cross-referencing the isotherms with the continentality to make sure that the range of temperature variation falls within what we would expect. So in order to do that, I took all of these data points and made sure that all of the isotherms actually cohere to the correct range. So each one of these is a measurement of the summer temperature and the winter temperature. And so, for example, in this instance, both the summer and winter temperature are 29, so we have a seasonal variation of 0, which is pretty much exactly what we'd expect at the equator. Whereas the closer you go towards the poles, the more marked the seasonal variation will be. Again, Artifactian goes over the whole algorithm that Ross Beggio worked out in his video. So on the whole, Tira is a little bit warmer than Earth. It has an average temperature of somewhere around 20 degrees, whereas Earth is, I think, 15 or so. I kind of envision the global climate and temperature variation as being roughly similar to the Cretaceous. You know, it's generally a pretty hot planet, but there are some colder areas towards the poles. I kind of think of it as coming towards the end of a hothouse period. Like in the period immediately following the mass extinction, it was very hot and climatically stable for quite a while. But with the recent series of intermittent eruption events, that has kind of destabilized the climate and led to some periods of cooling and kind of exacerbated the seasonal variation to some degree. And I guess we'll go over rivers now, because that's relatively quick and easy. You know, this is just a matter of marking in the drainage basins, which are informed by your areas of high elevation, and then looking at the precipitation map to see where the areas of highest precipitation are, and then just running a river through the lowland until you meet the sea. So this basin here is going to be very wet year-round, and this mountain range is going to block a lot of the moisture, so there's going to be some orographic rains here. So we've got several quite large rivers with lots of tributaries. It's a similar situation over here in the east, because this whole area, again, is constantly bombarded by precipitation and onshore winds. So this is probably going to be the wettest area of the entire planet, and all of that moisture is going to get funneled into this central river here. This is definitely going to be one of the biggest rivers in the world. Now, I'm still on the fence about this particular river, because as I have it at the moment, this is currently the longest river in the world. It's something like 6,000 kilometers long, so it's about on the same scale as the Nile. And I like the fact that it flows through this basin, which, if you remember when we did tectonics, we said this area was a failed rift. So it creates a natural section of lowlands for this river to run through. The problem is that the headwaters of this river are all the way down here in the south, and if we look at the precipitation maps, this area only receives precipitation during the southern hemisphere summer as a result of the influence of the polar vortex. So it's not really a great amount of water, and this river has to run all the way through this continental interior, which is very, very dry, and spoiler alert, is dominated by a big desert. So I really don't think this water is going to be voluminous enough to actually make it all the way through the continent without drying out first. So I'm probably going to end up getting rid of this river. And the specific shape of a lot of these rivers is kind of up to artistic license in a lot of ways, so I might continue to tweak those. And then, once we'd worked all of that out, we could finally make the proper climate map. And this is using the Köppen climate classification system, so the color coding corresponds with these climate zones. So a couple of points of interest. Number one, I was slightly dismayed by just how much of the land is taken up by deserts, because the red is hot desert and the pink is cold desert. And the reason why we have this section of cold desert sandwiched between these two areas of hot desert is because this area is where that mountain range is. And just as a result of the elevation, it just gets colder. And obviously it's not going to get much precipitation because the precipitation peters out as it rises up this slope. So, like, more than half of what was once the western continent is just taken up by one giant desert. But really, I don't think there's any getting around that, just because we are working with such large continents. There's only so far that precipitation can penetrate into the continent. The continental interior is pretty much always going to be dry. Also, because the planet is just hotter than Earth, the A-band, or tropical climate band, is significantly broader than it is on Earth. So like these blue climates, the dark blue is tropical rainforest, the slightly lighter blue is tropical monsoon, and the pale blue is tropical savanna. And on Earth, we only really see those climates within about 15 degrees or so of the equator. But if we throw out the latitude map, we can see that in our case it actually extends significantly beyond the 30-degree mark in some cases. So we've got three major areas of rainforest, one smaller one here in the west, one big one here bordering the Central Sea that's bang on the equator, and then a third one again in this eastern area that is just the wettest part of the planet. And towards the very northern edge of the supercontinent, we do get some temperate climates. Specifically along the western coast, we have some Mediterranean climates. So these are climates that are dry in the summer and wet in the winter. And that was very difficult for me to work out how to do, because it seemed very counterintuitive to my understanding of how circulation and precipitation works. Because the basic principle, again, is that land heats up and cools down faster than water. Therefore, in the summer, the continent heats up, which makes it a low-pressure zone, which encourages air and moisture from the sea to pass over it and make it wet. Whereas in the winter, the land cools down, and hence becomes relatively high pressure, and therefore the winds blow offshore, discouraging precipitation. So I didn't really understand how to make the opposite happen. But again, Ross Bay Geo came in and set me straight, and explained how, during the northern hemisphere's summer, if we say that this subtropical high is positioned directly over this part of the landmass, then it's not going to receive any onshore winds, whereas during the winter the subtropical high occurs more towards the continental interior in such a way that this whole stretch of coast will still receive onshore winds. So this yellow is CSA, which is hot summer Mediterranean, and this darker yellow is CSB, which is cool summer Mediterranean. Whereas on the opposite side, on the eastern coast, we have this area of, I believe, CWA? Yeah, CWA, which is dry winter humid subtropical, so it experiences the reverse, where it's dry in winter and wet in summer, which is more what we'd expect. And then in between the two of them we have some areas of uniform rainfall, so we have some humid subtropical and some subtropical highland here. And this, as of yet unnamed island here, also receives more or less uniform rainfall. Whereas Septentria, I was kind of surprised, because I've always kind of thought of Septentria as being mostly tropical, but it's actually a lot more seasonal than I would have thought. Most of it is taken up by CW climates, which are the wet summer temperate climates. Got a little bit of cold steppe along these parts of the foothills of the mountains that aren't high enough to become proper tundra or ice cap. And then again we've got some Mediterranean climate along the northern coast. And if we look at the isotherm map, if we just sort of keep in mind that Septentria is in this general area, then during the summer, the whole landmass gets between like 17 and 29 degrees, and in the winter it's somewhere between 5 and like 17 degrees. And the cutoff point for being considered a tropical climate is to be above 18 degrees in the winter. So it's possible that we might just get a very minor patch of tropical rainforest along this southernmost tip, but for the most part, the rest of the landmass is going to be pretty temperate. Now, as a result of the seasonal rains that we talked about earlier, where this whole stretch of coast has very strong onshore winds during the summer, but very strong offshore winds during the winter, we've got this very long, continuous band of CWA all the way along here, which is dry winter, humid subtropical. Whereas on the eastern coast, again, because it's just so wet all year, we have this area of humid subtropical that receives uniform year-round rainfall. Now, these D climates were a real pain to work out, because if you've seen Artifexian's videos, you'll know that if you work out the arid climate zones before you work out the D climate zones, the D climate zones can very often overlap with the arid climate zones, and so you need to do this special algorithm to work out whether or not this particular area should be a B climate or a D climate. And before I put the D climates in, pretty much the entirety of this southern part of the continent was arid. And so when putting in the D climates, I needed to check all of these areas to work out whether or not they should be reclassified as a D climate. I hope you're starting to see why it took me so long to make this. So the end result is that we have this strip of D climates along the southern coast, and D climates are, very roughly speaking, the sort of climates you see in northern Asia and Canada. You know, generally quite cold and dry, but with notable seasonal variation. And because this section here is right in the middle of the continental zone, it has some of the most extreme seasonal variation on the planet. So like in the winter here, this highland here gets up to, I think it's minus 29 degrees. So we have these patches of subarctic climate. And then these parts are monsoon influenced because, as I say, there is some precipitation during the summer because of the influence of the polar vortex. And while we're here, we might as well talk about Crescentia. So just like with this polar island here, I have changed my mind quite a lot about what exactly I want to do with Crescentia, because as I was originally envisioning it, I didn't want Crescentia to exist by the time of the modern world, because, I thought between the mass extinction and the continental convergence and the rising sea levels and everything else, there was plenty of opportunity to say that Crescentia has just slammed into another landmass, and just that the land that Crescentia used to be has just changed beyond recognition. But for one thing, I tried to have it join up with one of the other landmasses. I tried to say that there's been some sort of tectonic collision or something, but I just didn't like the way it looked. It just looked nicer when it was an island. And also, when working out the climates, you'll notice that because of the way these isotherms curve during the winter, because the isotherms tend to bunch up around the coastline, the very northernmost tip of Crescentia, which lies pretty much directly on the Antarctic Circle, is actually warm enough to receive a temperate climate. This is the only spot of, I believe, CFC climate on the entire planet, which is subpolar oceanic. So it's this one little spot of relatively hospitable climate that acts as kind of like a gateway to the increasingly cold, frozen wastelands of the rest of the landmass. And I thought that was cool enough to convince me to keep Crescentia where it is. So it will in fact remain an island. And then in this southwestern corner, originally it was mostly arid, but then Ross Bay Geo convinced me to put some orographic rains on the windward side of this mountain range here, and that made the whole subcontinent considerably more interesting. We have this whole mix of D-climates, as well as even this section of CWA, the dry winter temperate climate, alongside this smaller patch of cold desert. And then again, because of the way the isotherms bunch up around the coasts, we have this relatively warm zone along the western coastline. And again, Ross offered some invaluable advice about how to handle this bit, as he recommended that there be a subtropical high over here that bombards this coast with onshore winds that then deflect southward, which means we'd get this relatively narrow stretch of precipitation along the coast, again during Northern Hemisphere summer, whereas during the southern summer, the subtropical high would move over the northern part of this stretch of coast, which would block it from receiving any onshore winds and consequently any precipitation. So that means we get a chunk of warm summer Mediterranean climate here, and then south of that we get sections of temperate and continental uniform rainfall. Okay, and that is basically everything that I have worked out so far. Again, might still make a few very minor tweaks to it as we go forward. So at the time of recording, I am almost finished with the script for the first episode of the domestication/agriculture/anthropology series. And part of the reason that I haven't been able to finish sooner is because I needed to finish this map in order to have a better idea of where to place the cultures that we're going to be discussing in this coming series. So now that this map is more or less done, I should be able to finish the script pretty quickly, and it shouldn't take very much longer after that to actually get the episode done. So keep an eye out for that in the relatively near future. A final thank you to Ross Bay Geo, and Artifexian, and Madeline James, and Worldbuilding Pasta, and everyone else who knows more about physical geography and mapping than I do. Again, check out all the links in the description to find their stuff if you want to know more about the methodology involved. So thank you very much for watching, hope you found it interesting, and I will hopefully see you again very soon.